Yeah, another DraftPhysics.com video presentation. So continuing sort of on this kind of, I don't know, new subject. It's not exactly relevant to the dispute between kinetic energy, mv squared, 1/2 mv squared, and momentum as a true definition of energy. But certainly it's related, and I guess the bigger picture argument I'd make is one I've sort of I've alluded to in the past, that unfortunately it seems a lot of these experiments are engineered to validate positions, whether it's mathematics or whether it's some theoretical notion. The experiments are kind of shown, just to kind of protect one point of view. And so it is sort of, we're still stuck with science sort of quote mining the evidence and not telling the whole story, and attempting to minimize changes made or things done to the experiment that they are kind of implying are superfluous to the experiment, but they're really not. Like putting an audio tone on the radar experiment, different things I've complained about. And this has the same smell to it, of experiments that are engineered to provide the result, and they want to show you their ferrocell working. And they're not going to really explain that, oh yeah, it's a bunch of LEDs and they're all shooting at angles and the light's refracting and blah, blah, blah. So I'm not saying big conspiracy. I'm just saying it's just what people tend to do is they find the arguments that look the best and they try to make them look better than they maybe are. Maybe that part's a little bit of a cheat for a scientist. They ought to be careful about that. All right, so this series, I should play this whole video sometime. Maybe we'll do that. We'll play the whole video, and go through, because there's so many little lines in it that are just, they just say, you got to say more than that. That's not saying enough. So anyway, this is deriving a formulation for what happens in collisions between two objects. Okay, so that's still a little wet. So we'll wait a minute and then go to the blackboard just to explain the phenomenon that's quite curious. Okay, so the fact is that the experiment he does demonstrates essentially the creation of energy, in the sense that, by my definition, a certain amount of momentum goes in and somehow more momentum comes out. And that shouldn't happen. Just shouldn't happen. Logically, you shouldn't be able to just generate more energy that way. And so, but the experiment clearly shows it, so you can't deny the experiment, because in the sense that it's doing it. And it's doing it without any huge tricks, but there's a little gimmick. And so what I'm really arguing is that this is something about what springs do, and it's not so much about what objects do. And the spring can be in a different form, like compressed air. So I'm really getting to the experiment that I want to show, but I want to do this little piece of formula first stuff. So let's do the formula first. So he has written on the board, so at this point he has written on the board basically just momentum. All right, so you have mv of the initial object equals the mv of the initial object plus the mv of the other object you hit. So both, so if you have this much going in, if I hit into something bigger, I'm going to end up with the same amount of momentum, just in a bigger object. And so then he's going to take the, which surprises me, but let's go to it.
Goes into heat. Now I want to continue a case whereby I have a completely elastic collision.
So he says completely elastic, but the collisions won't really be completely elastic, and they're not hard things hitting each other, things that don't deform, things that don't store energy, because he's going to put a spring on them overtly. And in the case of a ping pong ball, he's going to rely on the compressed air inside the ping pong ball, frankly. So let's continue.
Q is 0. Momentum is conserved because there was no net external force. So now kinetic energy is also conserved.
Right. So he says these things, but obviously they're not conserved if you take the vectors at all important. Okay. So he thinks of momentum as this way and this way cancel each other out, but clearly, in an energy sense, this way and this way are both energy. So if you're making stuff move in any direction, it counts as momentum. That's what heat would be. Heat is going in all kinds of directions. You add up all the directions to say how much of an influence it is. All right, slight pause for a sneeze and such. Allergies. Anyway, so we have just momentum. The momentum has to be conserved to be the argument. And conserved means you can transfer it. So this is another thing, I don't know if it's worth drawing, but the idea is the momentum is some stuff going in a direction. Now if I hit something in front of me and I move it in exactly the same direction I'm moving, okay, then the momentum is still moving in that direction, you know, even though it's got another object. And so it's almost like this object is now part of this object, theoretically. The energy is still going in the same direction. And it's only when I start going in different directions that now I'm losing the momentum in the direction that the thing was going. And that's the part to recognize. So we call it conserved in the sense, and transferred. I've said before, you know, it's kind of a fudgy language about what's being said. But the real point is this has a certain units of movement. And it's the units of movement that you're just counting. And you have to have they have to add up. So let's go through this.
And so I can write down now 1/2.
So he's got momentum here, and now he's going to write a new equation for kinetic energy.
M1 V1 squared, that was the kinetic energy before the collision, must be the kinetic energy after the collision. 1/2 M1 V1 prime squared plus 1/2 M2 V2 prime squared. This is my equation.
So the prime is just the second object. Okay, so what's the second object going to do? So these are not objects that stick together, these are objects that bounce. So the prime is the second object, the not prime is the first object. Something like that. Well, the V1 is the first object. Yeah, there's a little one down here, and then these are the two. So this is the second object, this is the first object. Ugh. So anyway, strange. So now he's going to do this typical mathematical thing is where I have two separate equations with the same variables I don't know, which is V1 and V2. So I'm going to put the masses in, and I'm going to, you know, instead of doing that directly, which they could do in these equations. Well, anyway, they're going to use these two equations to solve for the V1 and V2. Now, the argument I would make is one of these equations we know can't be right. They can't both be accurate descriptions of energy. So I would argue the obvious one that's wrong is the one with the horrible history, which is the 1/2 mv squared. So you're just really taking a fake equation, you know, one that's just nonsense, and taking a good equation, and now you're going to use the fake equation to somehow establish what these variables actually represent. So that's when he comes up with
Number 1,
this
and this
formula.
is my equation number 2, and they can be solved. You can solve them, they're solved in your book.
Okay, so they're solved in the book. Too bad he doesn't, you know, of all the crappy math he doesn't do this. He doesn't derive the outcome of doing all your cancellations in here and figuring out what you end up with a result for V1 and V2.
I will simply give you the results, because the results are very interesting to play with. That's what we will be doing today. V1 prime will be M1 minus M2.
So V1 prime is after the collision. What happens to V1? So the first object goes into some collision. We're saying now V1 prime is what's it doing after the collision? What's its velocity?
Divided by M1 plus M2 times V1. And V2 prime will be 2M1 divided by M1 plus M2 times V1.
Right. So these are what's the second object doing? Okay, after the collision. So originally the second object in all these examples is going to be dead, stationary, so it's not going to have anything. And so what's it going to be doing after the collision? That's V2 prime. Okay, so these are the equations he's using, and he's going to show experiments that fit these equations. And the question is it true? The experiment, is it a real reflection of what the things would actually do if I took objects in the real world and did this over and over again. Would I get this result? My argument is, no, you won't. And it's only under special circumstances that you can force it to meet these formulas.
The first thing that you already see right away is that v2 prime is always in the same direction as v1. That's completely obvious, because the second object will stand.
So what's also completely obvious is that these two equations, one of them isn't a scalar and one of them isn't a vector, quantity. I mean, they're clearly, obviously talking about the same exact motion in the same exact direction. And so when they play the game that kinetic energy, when I have kinetic energy go this way and I have kinetic energy go that way, they don't cancel out. I add up all the kinetic energy. But if I have momentum going in two opposite directions, I play a game where I just cancel the two and say there's zero momentum, which is really bogus.
Standing still, remember? So if you plow something into the second object, they obviously continue in that direction. That's clear. So you see, you can never have a sign reversal here. Here, however, you can have a sign reversal. If you bounce a ping-pong ball off a billiard ball, the ping-pong ball will come back, and this one becomes negative. Whereas if you plow a billiard ball onto a ping-pong ball, it will go forward. And so this can both be negative and can be positive, depending upon whether the upstairs is negative or positive.
All right, so let's get to that example. He's going to bounce a ping-pong ball into a billiard ball. And so he's just doing the different cases here, so there's not too much of interest in the formula. It just keeps coming back. So we'll let him do this part because it's the obvious stuff.
I presume you have all seen it. Most people do this with pendulums, where they bounce these balls against each other. I will do it here with a model that you can see a little easier. I have here billiard balls, and if I bounce this one on this one, then we have case number 3. Then you see this one stands still, and this one takes over the speed.
Right, but we didn't quantitatively do anything to see that. But anyway, we didn't actually measure the speed. But that's the assumption. Now the trick is, in this experiment, okay, the one that is really bizarre, is that if he did it on this cradle, if he did it in this circumstance, I don't think he'd get the same outcome. And if he does get the same outcome, it would be a big surprise in the sense of the idea is you send just one cue ball in, okay, one ball worth of energy moving a certain velocity. And what you get out is more momentum in the sense that the two balls won't be going the same speed, but they'll be going 3/4 of the speed, which means they have more momentum. It's more momentum. And that shouldn't happen. And my point would be it's only going to happen if you put a spring on them. This moving spring is really what's going to make the difference. And so it wouldn't work if he used this. He wouldn't be able to show the formula working. So again, I'm just saying it's this use of selective experiments is kind of dangerous. Okay, so here's ping pong ball against billiard ball.
Ping pong ball off the bowling ball, the billiard ball. The ping pong ball comes back almost with the same speed, not quite, because the ratio is not infinity to 1, but it is 500 to 1, and the billiard ball will do practically nothing. That's exactly what you see there in case 2. But there we go. You see, the ping pong ball comes back almost as far as I let it go.
So it clearly does exactly what you would expect, which is this gets 1/500th. Okay, it's 500. The ratio is 500 to 1. So yeah, 1/500th. Okay, of amount of movement in the ball. So for a ping pong ball, it did pretty good. It moved the billiard ball quite a bit, considering how light, 500 times lighter, the ping pong ball is. It did a lot of moving. So in that sense, so obviously it bounces back with the same energy like a pendulum. So it does not quite, he obviously reaches to get the ping pong ball, so it's clearly not coming back with the same energy. So it's clearly lost momentum. I mean, it clearly loses almost a quarter, or you could say at least, an eighth, of its momentum, in the sense that it doesn't come back all the way back. It comes back a few inches short of all the way back.
And
all right. So anyway, but the more important one is the opposite reaction.
The billiard ball
we'll get
almost
to that
does nothing. Now comes case number 1. That's the non-intuitive case. It is intuitive that if the billiard ball hits the ping pong ball, that it will continue, as you will see, v1 prime is v1 with the same speed. It's not at all intuitive that the ping pong ball will get twice the speed of the billiard ball. And of course,
So twice the speed, he's arguing. And so it's if you use two masses that are just one's twice as much as the other, you're down to 3/4 of the speed. So it's only twice the speed if one of them is almost infinite. So that's the highest you can go, is the 2 number.
Of course, you cannot see that quantitatively because we don't do a quantitative measurement of the speed of the...
Right, so he's pointing out how, yes, no, we didn't bother doing the experiment accurately, which is kind of a silly thing to admit, but anyway.
Ping pong ball, but you will see that it bounces up quite high. So there we go, the billiard ball onto the ping pong ball. Look at the billiard ball alone, forget the ping pong ball.
Well, all you can look at is the fact that the ping pong ball obviously leaves the billiard ball much faster than the billiard ball swinging, because the billiard ball swinging and the ping pong ball is gone. So if it was going the same speed as the billiard ball, then it would move with the billiard ball. So it's clearly moving faster than the billiard ball. So it clearly gained more velocity than the billiard ball has.
And try to see that the speed of the billiard ball is practically unaffected by the collision. That's what you see there. V1 prime is V1. You see?
Well, you're clearly not going to see how unaffected it is. So clearly it's only moving something 1/500th of its mass, which isn't going to take away much, and it's going to be hard to see at that tiny a percentage of a change in its total momentum. All right, but the ping pong ball obviously goes away with twice the velocity. It seems at least twice the velocity, okay? It goes definitely... by just the other example, it goes twice as high, blah, blah, blah. So it's clearly more velocity goes into the ping pong ball. Now, my point would be, this experiment should work the same if I take the air out of the ping pong ball, right? So if I make the ping pong ball less of a spring, right? If I take away its capacity to store energy, then it still should work. The formula is about the fact of the masses and the velocities. The formula is not about whether this is elastic or inelastic. So it's kind of hard to say that a ping pong ball is an elastic object when in fact it does bend, deform, and then spring back. And so the argument is if I take the air, if I put a little hole in the ping pong ball, it'll make it a dead ping pong ball, and it won't bounce with the same velocity. It won't fly off. It'll just kind of stay with the billiard ball. That would be the conclusion, that it will just be, a very dull bounce. It'll reflect with the same velocity. It won't be able to absorb the double velocity. So it won't work. And that's the fact. So this is a selective experiment. If he made these truly elastic, that is, two hard objects, he won't get the same result. And so, this is the shenanigans of how they do these experiments. All right, so this one, he's setting up these two cars to do this experiment.
Elastic. And the way I will do that is by using springs, which are...
Dear Power, you beat deep in the heart of our hybrid. Thanks to you, we slice through curves.
Which are attached to each mass. And to an object and two will be...
I want to go back a little bit just so you hear his... See, it's very subtle, he just slides right over what he's doing. And, okay, so he's saying, okay, let's do an elastic collision experiment. And then he says, that's hard to do. That's pretty easy to do, right? You just take two things that can't be deformed or can't store energy, and you bang them into each other. So what's so hard about that? I did want to say about the commercials. It's kind of, I got a copyright violation for playing his video, which is pretty annoying, right? So it doesn't, it doesn't hurt my account any. It just means I can't monetize the video, blah, blah, who cares? But the very fact that you get a copyright notification for clearly fair use of a physics lecture is just sort of bullshit.
In my mind. I'm going to have one object M1, which I bang against object M2, and object M2 will be standing here, will have no speed. Object M1 comes in from this side, and I'll try to make the collision elastic. And the way I will do that is by using springs, which are attached to each mass. And springs are conservative forces. So there's almost no heat that is generated in the springs during the collision.
Right. And so even though these people keep saying that all this energy gets lost somehow with springs, clearly how does it get lost? Where is it? It can't go anywhere. He just says it's completely conservative. It doesn't make any heat. You don't lose the energy. So how does that explanation work? Well, anyway. But clearly, all right, just these pieces of metal, if they just put, metal, hitting metal is elastic. So he should just do the experiment with just, put a ball bearing on the end, have the two things hit with in an elastic manner, and do the experiment. So the idea is the spring, here's the gimmick. And so the spring is really the object that's going to create this as being possible. It wouldn't happen without the spring is the point. You can't do the experiment without the spring and have the same result.
And so to a reasonable approximation, you will get an elastic collision. But of course there's always air drag.
So in a reasonable approximation, no, it's an unreasonable approximation in a sense. Because if you want real elastic, you just put ball bearings on the ends of the things and let the ball bearings hit each other and you have perfectly elastic, and that's how you should be doing the experiment. And then you could even put a piece of paper in between and just have them hit each other and see if the paper burns or something. Yeah.
Never take air drag out. So there's always some external force on the system. So momentum is never exactly conserved, and kinetic energy is never exactly conserved.
See, they're saying exactly conserved, but of course it is conserved. It's always conserved in the absolute sense in that you're either moving air molecules or you're moving internal molecules creating heat, or you're moving something. Oh, it always has to go somewhere. So it's always conserved. The argument is it 100% transferred? Can you 100% transfer energy? And the fact is you're not going to likely be able to 100% transfer it, because you're always going to create a little bit of noise in the process. It's hard to find the no resistant wire sort of thing. It's the unusual circumstance where you have the superconductor.
Here, so it's only an approximation. So I have one mass of unit 1. I will tell you what that is, and I bang that into number 2. And the masses that I have, one mass.
Okay, so they're just double, so we've already done some of this, and so we'll just get to the experiment itself. And so the calculated numbers are just based on his formula. Okay, so he goes back to the formula. I'll just play that a little bit. So he's going to figure, he's going to put in his mass numbers. Now he has the mass numbers. He'll put the mass numbers in, and that'll give him a prediction for the velocity.
No surprise that it bounces back. So that's minus 1/3. And when we look here, we have 2 times 1 divided by 1 plus 2 is 3. That is plus 2/3. So number 1.
Okay, so the first object bounces back at 1/3, and the double mass object goes away at 2/3. So the argument made is that if it's double mass, it really should be half the velocity, not 2/3 of the velocity. So 2/3 of the velocity means in that one package, the larger object, you actually have more momentum than you started with, which is, you could argue, paradoxical or free energy. But the key is in the argument that the spring is what's creating this phenomenon. And so it just happens to be an advantage of springs. And it may be one that it sort of is free energy. It's hard to not argue that that isn't free energy. I mean, the theory is the bullet could go in, okay, going 250 miles an hour. I hit it into a larger bullet, okay, and it transfers what is more momentum. I mean, the real number gets larger in terms of the real momentum of the heavier object. The bullet leaves at 3/4 the speed, so it's going slower, but it's a much heavier bullet. So the fact is that it will generate more electricity, or it will generate more heat, or it will generate more anything because it has more momentum. So you can't deny that fact. Now the trick is that you do send some energy this way, 1/3. You have 1/3 extra going this way, and you have 1/3 extra going that way. And that's the real argument, is what is the consequence of that extra 1/3. Like I said, if we were in space, it wouldn't matter, but you sent 1/3 this way and you sent 1/3 extra that way, so the two cancel out. if you're navigating a spaceship. But from our perspective, all you really care about is how much energy you're sending that way. And in that sense, you sent more energy that way. And that's sort of free. It's a turbocharger. So in a sense, you can say springs are turbocharging the interaction by somehow using the energy twice. It's a real, it's something like that actually.
Will come back with a speed 1/3, which of course, since this is sign sensitive, we get 1/3 v1, and this one is plus 2/3 v1. That's the prediction. And the way we're going to measure it is by measure the time for the objects to move over a distance of 10 centimeters. No matter how long you see these cars to be, there is here a piece of metal which is 10 centimeters long. It goes through a slot with a diode. We have one system.
Okay.
Whatever comes out
Skip that.
should be the same as this. So let me move this up a little.
Let's get to it.
If it is negative, it will go back through the same slot. And the electronics is arranged in such a way that when it goes back through the same slot, that it will initiate this time. You ready? I hope you know what you're going to see. This one will come to a halt, and this one will go on. They have same mass.
All right, these are the same mass ones, so we already know. Well, we'll go ahead and play it. What the hell is
There
it?
we go.
The obvious happens.
This one is indeed coming to a halt.
That one stops and the momentum goes forward, and by some standards you could say, okay, this is 196, so it's a tiniest bit slower than the first one. Just very, very tiny difference. So tiny not to be taken seriously almost. All right, now we get to the oops. Fingers are all broken today. All right, so this one's the heavier car. So now he's going to bang this car, the lighter car, into the heavier car, the twice as heavy car. And the twice as heavy car is going to leave with 2/3 the velocity, which means it's going to have 1/3 more momentum than the initial car had, which is like, where did you get that from?
ID 0. Okay. You ready? Yeah.
It looks like a different kind of springs on these things. Actually, it looks like the bent metal type springs. I mean the band springs.
There we go. Okay.
All right, so you have the initial time. This is 186 is now the velocity, so it's a little bit slower. So the higher the number, the slower it's moving. So it's a little bit slower, but it's not what it should be, which is half as fast. So the twice as heavy object left with more than just half the velocity, which means it gained momentum. And the other object moved back in the opposite direction at the slow speed, 1/3 the initial velocity. And my argument is if he didn't have the springs on those cars, this wouldn't have happened.
Now comes the real acid test. 1, 2, 3, 186. 1, 2, 3. That was indeed extremely close to elastic collisions, in spite of all the problems that we have air drag.
So the numbers come out to 125, 124, all matching the 123 number. So they're all, when you multiply by 1/3 or 2/3, you get the same number, which indicates, okay, that's a valid outcome. All right, so now you're stuck with just how do you explain that? And so all I've been able so far to do with that is to first notice that the springs are what's made it happen. So if I did do it with pendulums, I couldn't make this happen. I can't create this extra energy, because if I could just make a stream of pendulums where you just keep banging something into something twice as heavy. The pendulum just keeps banging into something twice as heavy, and it would just keep generating 1/3 more energy each time. And so after you go through 10 sequences of that, you've ended up creating whatever, twice as much energy as you started with, or 4 times as much. You're gaining 1/3 each time, so all you have to do is go through a couple of renditions before you've doubled your energy. And that's very interesting, right? I mean, why wouldn't we capitalize on that? Have to pause again, I think. Yeah, it should be back. Let's make this full screen. All right, so the simple scenario is you have the momentum. So let's just say it has 100 as its momentum. You know, if you figure out the mass times velocity, it's 100. Okay, so mv equals 100 of this object moving in this direction. It's got a spring on it. Okay, it's going to hit another object with a spring on it. Okay, this object has twice as much mass. So we'll put a 1 and a 2. And the fact is it's going to leave, when I do the mass times velocity number, it's going to leave with 130 momentums. Okay, and this object is going to bounce back with 30. All right. So clearly the two 30s, you could just cancel them out, and then I've conserved the momentum. Then I have 100. So I've transferred the 100. So it's the extra 30 going this way, and the 30 going this way. That's the part that shouldn't be there. And the argument is that what we don't, what's not recognized is essentially the spring becomes whatever it's attached to. So the mass of the spring itself is the mass of the entire object. So once I attach a spring to an object, the center of the mass of the spring now becomes somewhere inside the object itself. So now the spring is just part of the object. And the fact is I'm going to compress the spring essentially for free. Essentially the compression I get in the spring is still pushing energy that way. So when the spring hits and starts to compress, with each bit of compression, it's pushing on this object. So the more and more it's compressing, the more and more it's still pushing. So the initial momentum, when it goes in, is compressing the spring without using any of the energy. That is, the energy is not getting used up compressing the spring. The energy is imposing pressure on the other object as the spring compresses. The spring couldn't compress unless this object felt the pressure of the spring pushing against it. So the spring is compressing in the same direction that the momentum's going. So you compress the spring, the motion is still in the same direction because the spring is pushing in that direction. So you're still pushing this object just as if the spring wasn't there. And you've compressed the spring without this object knowing the difference. From this object's perspective, it didn't matter that the spring compressed because it's this guy's problem. Okay, the spring compressing is happening to this object. It's not happening to this one. So it's effectively transferring the energy, the momentum. So this one gets 100% of the momentum, and it never felt any of the spring's compression because the spring is moving, not because you're pushing into a non-moving spring. So the spring's momentum is essentially being decided by whatever you attach it to. And essentially you're compressing it for free. So now you've compressed the spring for free. It didn't cost you anything to compress it. You've transferred the motion, the momentum, and now, okay, that this has sent all of its energy into this object. Now the spring is compressed, and now the spring uncompresses, and that's where you end up pushing both objects, okay, with the spring's explosion. The spring now explodes, okay, to release its energy, and it pushes this one the 30% extra, and the 30% extra going the opposite way, this way. And so now that's where you get the extra energy from. So if they did this with real elastic objects and no spring, my argument is it won't happen. You have to have some mechanism to store the compression. So without the storage of the compression, you're not going to get the same result. Exactly what you're going to get, I'm not exactly sure either, but I just know that if I do this on a Newton's cradle, you can sort of get the idea that if I have a row of steel balls, and I send in one, I'm going to get one out this end. I'm not going to get one plus something, 30% more. So, if I take this now and I take a if I make a lighter, a half size one, right, I'm not going to get, this one's not going to have more momentum. So when this little half size one hits, it's not going to make this one leave with 3/4, yeah, 3/4 of the same velocity. Because if it did, this would be more momentum this way. And when it came back down again, right, because you gained momentum, 3/4 is more momentum. So you went from 100 down, you hit it with 100, you have 130 here, right? So you have a half size object hits, it sends off this object at 3/4 the momentum. So I guess you could get rid of these. Well, these help just to force the action and actual reaction to happen. Now, what's the trick is that this one's going to bounce off with 30, and that means it's going to stop here and then come back down, and the rate, the period of this oscillation is going to be different than the period of this oscillation. So this one's going to be coming back down when this one's coming back this way, and that's going to cause trouble because they're not going to be in sequence. So you can't just visually see this happen. But anyway, just think what the realization of their theory would be is that the 1/3, the 3/4 means that I have extra momentum, and then that extra momentum would come down with 130, right? It would hit with 130. So this little one would have to leave, okay, with 130 momentums, or it has to leave with this one having, because it's hard to increase the velocity, this one having some percentage and then this one moving also, so this one would leave with just the 100 and the 30 would end up being here. Right, but that wouldn't matter because as these two, if they hit this the same time, if you got the period, the timing right, if they hit here the same time, well, now they're going to create 160 at this side. You know what I mean? So each time you go through here, you'd end up with 130, and then you're going to end up with what, 170 something, at 3/4 each time. So you're gaining 3/4 of the energy, so you'd have 178, and then by the third time, you'd be at 240, whatever. And you just keep increasing the amount of energy perpetually, because you could just keep sending more and more, depending on how many steel balls you put in, you could just keep sending more steel balls up. So, it just doesn't work. It can't be the truth. And I'm just saying that, and then you could just, obviously it doesn't work in the sense that Newton's cradle won't do it. But if I put springs between each one of these, then theoretically it should do it, because it just did it on the air track. It's undeniable that it works. And the only thing you have to take care of is the fact that the stuff swinging back this way, you have to make it swing back crooked so it doesn't come back and hit the steel ball. So as long as I get rid of the swing back energy and just use the extra momentum I create on the other side, and everything stays normal over here, then I'd be fine. And I can just keep creating more energy, theoretically. Something like that. Well, I'm just saying you can see the paradox created. The paradox in the sense that it appears to be free energy. Now, whether somebody can actually make a system where they take advantage of it, it is, like I said, it's undeniable fact that the experiment using a spring connected to the objects it's moving clearly provides you an opportunity to make more energy go in the one direction. If you don't count the energy going in the opposite direction, the 30%, if you get rid of that, you're clearly gaining energy in this direction. And so if you create a system where you just keep doing that, so you take a mass, you take this air track you just did. All right, yeah, that's probably a better way of saying it. So we'll say it that way. We'll illustrate it that way. So let's say he could make that air track really long. Okay? So it's a really long air track. And he starts with 1 kilogram. All right, and he puts that on the air track, and he's going to send that with a velocity. Okay, and we're going to say that's going to start off with 100 as momentum. So the velocity times the weight will be 100. It's just an arbitrary number. It doesn't really matter. And he puts springs on everything. So then he bangs it into something twice as massive. with springs. So we're going to get 130 joules or 130 energies in this object, momentums. Okay, and then we just collide that into an object that's twice the size. It also has a spring on it. Okay, now that object is going to be the original 130 plus 2/3. So one third of 130, which is whatever it is. 1/3 of 12 would be 40, so 42, let's say 43. So we had 43, so we have 173. So now we have 173 joules here, our momentums, whatever you want to call them. And I could just keep going, right, by just 2xing the mass, and keeping a spring between them. I can go from 100 to 173, and then theoretically I can just keep going, right? I can just keep making the mass heavier and heavier, okay, 2xing it, and just keep increasing this number. And clearly I could easily double it or triple it or quadruple it by just going through these series and eliminating all the friction and completely ignoring all the action back this way. The only action I care about is this action, and this action would constantly be getting increases in momentum. So it is free energy, frankly, made out of springs somehow. And like I say, I have to ponder it some more, but I don't see why theoretically that couldn't work. So if you had a very long air track, so you'd have to, obviously it's too much trouble to maintain an air track, so there has to be some other way you're transferring the energy, pendulums, whatever. Yeah, pendulums that have a, where the placement of the objects is displaced, so this action doesn't go back the same way as this action. So the reaction won't hit the other object. The action goes to this object, and then the action goes to this object, and the action goes this way. And that way you get rid of all this negative stuff going the wrong way. You get rid of the opposite reactions and just count the forward action. So you can make a pendulum that's staggered in space, where the balls are here, 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 and you move them at an angle into each other. And you should be able to progressively increase the momentum of the objects rather efficiently, actually. I mean, certainly 1/3 gain in the energy, 1/3 gain is a lot more than you're going to lose in terms of friction, noise, air resistance, all of that stuff. 1/3 is a huge amount of energy. So anyway, just curious. Very curious. So, again, like I said, it doesn't really have anything to do with the dispute between kinetic energy and momentum, because both of them are broken by this process. You lose kinetic energy, you gain momentum. So both of them, neither one of them are sensibly conserved in the experiment, in the sense that the stuff going in one specific direction isn't what it should be, which is, interesting. So is there anything else to say? Yeah, so it's just interesting. It's a little distracting, frankly. I don't know if I'll be talking about anything else for a couple of videos, just because until I come up with more of an answer. Clearly, like I said, the spring is critical. Without the spring, it don't happen. So the spring is making it happen. So springs are critical. Moving the spring is even more critical. The fact that the spring has a momentum, and the momentum is essentially whatever weight you tie it to. So you can make a spring have more energy by tying it to more mass. And you move that, the spring gains a lot more potential energy, in the sense that it has more potential to store energy. And that's very interesting. But that's all I can say about it at this point, is it's very interesting. Yeah, I really don't think there's nothing after this that Bissane just does the objects sticking to each other experiments that are all quite none of them create any of these. None of them create this paradox of, well, you had so much momentum going this way, and now you have more momentum going this way. And you didn't add any energy. You didn't push any extra in there. I mean, a turbocharger isn't even a good example because turbocharger's taking energy you were losing as heat and other things and putting it back in the stream. So you're taking back some of the losses. The spring isn't taking back losses. And so it's a little bit inexplicable. So I won't explicle. Alright, so we'll leave it at that. Call that a video, and yeah, I don't want to get obsessed with it. This is an interesting curiosity. It really doesn't have anything to do with the fundamental dispute, and I want the fundamental dispute to be the focus, because that's the important part, that kinetic energy is nonsense. But anyway, so till the next time. Well, and also the other part to point out is how the experiments are clearly engineered. We're using a ping-pong ball, not something light that's hard. No, a ping-pong ball, because it bounces. Yeah, and then it's a spring, and then we have springs attached to the cars. Instead of letting them kinetically bang into each other, elastically bang into each other, just metal on metal. Why the change? Why put a spring? Because it's the only way that works. Simple answer. Alright, we don't need this. I don't know why I do that. That's curious little mechanical habits. So, this has been a DraftPhysics.com video presentation. Till next time and such.